Okay, welcome to lecture. And like I said earlier, we're just going to continue on lecture a little bit more through here in electrochemistry, electron configuration, and some quantum numbers, just to make sure everything kind of gets tied together. And that'll be it. Again, we're going to move the experiment that was scheduled for today, which is experiment 3, to Tuesday, because I think on Tuesday it's just going to be a lecture, and that little lecture will be moved to Thursday, where it goes with the significant figures, so that'll all work out okay, I think. All right, so any questions before we begin here or continue talking about what we've been talking about here? Again, electron configuration, quantum numbers, how they all kind of come together. Any questions so far? Okay, then let us continue on, might as well. So we did number 2 there in periodic table. So might as well continue on there. We got lithium, which is number 3. So again, as we saw, we would continue always at the top there, that little zigzag guy that we made. And that means that we would start with 1s2. And as we saw with our helium orbital diagram, that 1s orbital was full. So then we got a zigzag back. And the next place that we would end up with as you zigzag back is 2s1. Now, in terms of our orbital diagram, we can draw 2 boxes, one for the 1s orbital, one for the 2s orbital. This is clearly not correct in terms of energy. I'm just going to draw it left to right. Normally you would draw it higher, but I don't want to run out of room. So not correct in terms of energy, but good for our purposes here. Again, the first one is always going to go in upwards. Second one is going to go in down to pair off. And that means that the third electron here would go in the upwards fashion. So we've done the quantum numbers really for these first 2 when we did helium, which was before it. So if we want to look at the quantum numbers for this third electron that's present, so why don't you take a second and write the 4 quantum numbers for that electron and see what you come up with. Okay, so if we go about the 4 quantum numbers, again, remember that we can use the first number here, which is 2, and that should tell you that n is equal to 2. That means that for L value, we could have 0 or 1 in this particular case. And I'm going to ask you, is both of those numbers correct? And if you put both of those numbers down thinking they are correct, they actually are incorrect in this case, based on the electron that we're dealing with. Remember that the 0 represents an s orbital, the 1 represents the p orbitals, and we could clearly see that this electron is actually in the s orbital. So the only acceptable value for L for this guy would be 0. So it should only be 0. It cannot be 1. 1 is available because technically we're on the second energy level. And on the second energy level, we do have p orbitals available to us, but we're actually not using them yet. So can't have an L value of 1 for this one. So for this particular electron, it should be n is equal to 2, L is equal to 0, which means the n sub L should also equal 0. And this guy has a m sub s of plus 1/2 as the spin is going up. So again, even though those orbitals are available, since we're specifically talking about this electron, We're obviously are in an s orbital, which means we should only have the L value of 0. Any questions on that one there? So continue on to beryllium, which is 4. Again, starting at the top, it would be 1s2 and 2s2. Our diagram here would be 1s and 2s. So 1 up, 1 down, 1 up, and fourth one gonna go down. Again, the first 3 electrons will be the same quantum numbers as we did previously. So let's just focus in here on this guy. So this electron here would have an n value also of 2. It is still in the s orbital, which means the acceptable L value is 0 for this guy, just like the other one. The m sub L for this guy would be 0. And what's going to give it a different set of quantum numbers is the spin is going down. So he would be -0.5. Again, allowing both of these electrons that are sharing this orbital to have 4 different quantum numbers. Really just the spin part's different, and that's good enough. And again, that's what basically Pauli's exclusion rule tells us. Question on that there. All right, continuing on to number 5, since we got a nice rhythm going here, let's go with 5 is boron, they say. So we're going to go 1s2. We're then going to go 2s2. And as we saw here, we have now filled up our s orbitals, or 2s orbital. The next place we should end up is 2p1. You count up the top numbers, 2, 4, and 5, which is good. Our orbital diagram here we'll have a 1s box, a 2s box, and because it's a 2p subshell, there's 1, 2, and 3 boxes that you should have. In terms of how they fill, they're going to fill like we've been doing, 1 up, 1 down, 1 up, and 1 down. And the first electron over here on the left is going in the upwards direction. As we've been seeing here, these first 4 electrons, we've already done the quantum numbers previously. So if we now focus on this one, so take a shot at it, what should be the 4 quantum numbers for that electron right there? Okay, so you can approach it the same way. We know it's sitting in a 2p orbital. So that again is going to give us our n value of 2. And just like above, that means technically we could have L value of 0 and 1. And as we've been talking about, that is our s orbitals, that's our p orbitals. So we could clearly see that this electron here is in a p orbital, which means the acceptable value here for L should only be 1. So for that electron, we should have an n value of 1, n value of 2, an L value of 1. Now, as we talked about previously, if you have an L value of 1, you could have an m sub L value of -1, 0, or +1. And in this particular case, since we're talking about a specific electron, remember that these orbitals go just like this, -1, 0, and +1, which means we could clearly see that our electron is hanging out in that -1 orbital. which means the M sub L here should be -1, and the M sub S would be +1/2 in this case, as the electron is pointing upwards. Any questions on how I got to any of those numbers? All right, then continue on number 6, which is carbon. So carbon will be 1s2, 2s2, 2p2, 2, 4, and 6. Again, with our orbital diagram, 1s, 2s, 1, 2, 3 for our p. 1 up and 1 down, 1 up, 1 down, 1 up. And now we do have some options where we put our 6th electron here. And there is a rule that's down in your notes a little bit. It's known as Hund's rule. And Hund's rule basically says that the most stable sort of configuration for an atom is one where we have maximum number of parallel spins. So parallel spins means we're heading in the same direction. Paired spin is opposite. So this is paired. And parallel is going in the same. So what that means is when we have multiple orbitals in a subshell, the electrons actually go in one at a time, heading in the same direction first. So they'll go 1, 1, 1, and then come back and start pairing off. And that's what's known as Hund's rule, maximizing the parallel spins of those electrons makes it more stable. So that means that the 4 quantum numbers for this electron should be n is equal to 2. It should still be L is equal to 1 because it's in a p orbital. And now the M sub L value should be, again, it is -1 for this guy, 0 and +1, which means the M sub L should be 0 in this case, as it is sitting in this orbital. And the M sub S would be +0.5. Question on that there.
How do you determine L again?
How do I, L?
Yeah.
Yeah, so L could have values of 0 to n-1. So n in this case was 2, which means you could have values for L of 0, and 2 minus 1 is 1.
Oh, okay.
And then again, each of these little numbers here represents a specific orbital. Again, 0 represents S, and this guy represents P orbitals. And if you get to 2, it is D orbitals, and 3 is F orbitals, and so forth.
Okay.
Other questions? Okay. So then let's continue on to number 7, which is nitrogen. And nitrogen should be 1s2, 2s2, 2p3. Again, counting the top gets you to 7, 2, 4, and 3 to 7. And here in our orbital diagram, again, not perfect in terms of energy, but they normally should go up. We go in 1 and 2, 3 and 4. And again, following Hund's rule, 5th, 6th, and 7th electron should go in there. And at this point, our n value for this guy should be n is equal to 2 still. L is still equal to 1 because it's a p orbital we're in. And now for the M sub L, again, remember, it just kind of runs in order. So this is -1, 0. And we now see that that electron is hanging out in the +1. So that would be our M sub L is equal to +1. And lastly, our spin is going upwards. So that would be +1/2 in terms of the spin. Any questions on that one? All right, we're close to the first 10. Might as well finish it out. So oxygen is 8. So why don't you take a couple of minutes here and finish oxygen, which is 8, fluorine, which is 9, and neon, which is 10. And for each of them, do the electron configuration, the orbital diagram, and for each of the last electrons in each of these, just the last electrons, do the 4 quantum numbers for the last electrons for each of them. So take a couple of minutes and then we'll go over it, see what you come up with. Okay, let's take a look and kind of see how we're doing. So we'll start with the oxygen, which is 8. So in terms of electron configuration, 1s2, 2s2, 2p4, looks like a winner on that. And our orbital diagram, again, we'll need a box for the 1s, a box for the 2s, and 3 there for our 2p. We're going to go up, down, again, 100 rules, so everybody's going parallel. At this point, they got nowhere else to go, so we're going to come back this way. That means that this guy here would be our last electron. So in terms of its quantum numbers, n would equal 2, again on the second energy level. It is in a p orbital, which means L would equal 1. M sub L would equal -1 as it's in this first orbital that's present. And the spin that we see now is it's going down, which means it's -1/2 in terms of its 4 quantum numbers for that last electron that's present. Question on that particular one there. All right. Coming to fluorine, which is 9. So we have, as we can see here, room for a couple more electrons there in the p orbital. So fluorine would be 1s2, 2s2, 2p5, giving us our orbital diagram of up, down, up and down, and up, and down, making this the last electron that technically went into that orbital, or that actual atom. And the n value here would also be 2. Again, it's on the second. Still hanging out in the p subshell, so L would equal 1. Specifically in that p subshell, it is in the 0 orbital, right, for M sub L. And our spin on that guy also going down, which would be -1/2 in that particular case. Any questions on that? And lastly here, neon, which is 10. And that means we got 1s2, 2s2, 2p6 in that case, and that gives us 10, giving us a 1s orbital, 2s, and our 2p subshell going up and down, and 1, 2, 3, 4, 5, and 6. Going up our 2p orbital, obviously we need to go further if we have more. And that also means that this last electron here, still on the n equals 2 level, still in the p orbital, so L would equal 1. And again here, in terms of specifically what p orbital, it is in +1. So our M sub L would be +1, and our M sub S would be -1/2. Question on those first 10 electron configuration, how to do orbital diagram, how to, as you can see, be very specific about quantum numbers and the ones that are present. Any questions on any of those there? All right, so why don't you do calcium, and why don't you do electron configuration for calcium? And while you're at it, why don't you do the quantum numbers for the, let's just randomly pick. Let's go with the 16th electron in there. Why not? Number 16. 16 electron in calcium. What are the 4 quantum numbers? If you want, you could just do the electron configuration. You don't have to do the orbital diagram. So what is the electron configuration? And while you're at it, what is the 4 quantum numbers for the 16th electron that went into calcium? All right, so let's take a look. So we'll start with calcium, which is 20. I guess I could have told you that in case you didn't know. Hope we got a periodic table somewhere, right? So that means it has 20 electrons. So in terms of this configuration, we are looking at 1s2, 2s2, 2p6. That's 10 if we count up the top. 3s2, 3p6. That is 18. And then we should go again here to 4s next, and it would be 4s2. Remember, there's that difference in energy. When the electrons go in, the 4s actually is lower in energy than the 3d. So electrons do go into the 4s first, and then into the 3d. And by the way, what we're talking about here, and pretty much what you talk about in most of your chemistry classes, when you do write electron configuration, is the electron configuration based on filling order, and that means lowest energy to highest energy. You will sometimes see it if you Google around in some places. You'll actually see it where everybody's sort of in order. All the 3s are together, all the 4s are together, and stuff like that. And sometimes that is written that way because that is really based on energy after the electrons go in. So what happens when we fill the electrons, they do go 4s first and then into our 3d. But once you start actually putting electrons into the 3d orbital, there's actually a switch that occurs, and the 3d ends up being lower in energy than the 4s. But that's only after you get some electrons in those d orbitals. And that's why sometimes you will see electron configuration almost written in order. And usually it's not correct for us because we do it in filling. And probably 9 times out of 10, if you write electron configuration, it's done based on filling rather than energy, but you'll sometimes see it that way. This will play an important role in what we'll talk about in just a second, sort of that switching of those orbitals in just a second here. We are looking at 16 in terms of electrons, so that's 2, 4, 10, 12, and then 4 in here. So our 16th electron is hanging out right there. And technically speaking, that's a p orbital. And we have 2, 4, 10, 12, which means we need 13, 14, 15, 16. That's 4 more electrons. And that means technically the way they do go into that 3p orbital, this electron right here would be number 13. This one would be number 14. This would be number 15. This would be number 16. And this would be 17 and 18, which would fill it up. So really, when we're talking about the 16th electron, it is actually this one right here. And this is going to help us determine some things. This should help us determine our n value for that electron. Our n is going to equal 3. And since n can equal 3, L could have values of 0, 1, and 2. And in this particular case, the correct answer for L is 1 in this case. That is correct because that is in a p orbital, so it should be only 1. So L should be 1 in this case. And M sub L, because it's hanging out over here, should be -1. And lastly, the spin on that guy is going downward, so it should be -0.5. So for that particular 16th electron right there, those technically should be the 4 quantum numbers that go with it. Question on that there. Question on quantum numbers, electron configuration. Now, when we're looking at something like calcium, if we just look at the electron configuration for it, and if we look at the first part of it, from like here to where I boxed. And if we count what's in the blue box in terms of electrons, that is 2, 4, 10, 12, and 18 electrons. If you go to the periodic table, number 18 is argon. And we can write a kind of shorthand for electron configuration where this would be argon in brackets. And that means the electron configuration for argon. and we would continue on with the rest of it, which would be 4s2. Argon is a noble gas, and this is sometimes what is referred to as the noble gas configuration, where, much like the name implies, in the brackets should go a noble gas. So it should always be the noble gas that in the brackets, the noble gas that comes right before the element on the periodic table. So if you were doing sodium, which is 11, you would back up to neon on the periodic table, which is number 10. And if you were doing sodium, you would do neon, and then you would continue on with the configuration, which would be 3s1. Again, this would represent neon's configuration. And again, you can do that for everybody that's there. You know, krypton. And that is 5s2. And if you're not sure who that is, that should be strontium, number 38. It'd be who that is. So again, you could do this sort of shorthand, which is usually the noble gas configuration is what you want to use. And again, the noble gas that comes right before the element goes in the little brackets, and then you continue on with the configuration. Any questions on how to do that there? So clearly you need to be able to write an electron configuration. You need to be able to write noble gas configuration, orbital diagram, identify quantum numbers. Since we're talking about some things here, what happens if we do have something with a charge? You do have to adjust your electron configuration for things with charges. So for example, if I had, let's say, we'll go with magnesium with a +2 charge. Magnesium, if you look on the periodic table, magnesium with no charge has 12 electrons. Because it has a +2 charge, the positive means it lost electrons, right? Becomes a cation. 2 means it lost 2 electrons. So I think we talked about this when we talked about protons, electrons, and neutrons. That means that our magnesium here would have 10 electrons. And if we write the configuration for magnesium with a +2 charge, 1s2, 2s2, 2p6. If we look at something like nitrogen with a -3 charge, nitrogen with no charge has 7 electrons. The -3 here, minus means it gained electrons, 3 means it gained 3 electrons, so that is 10 electrons, which means nitrogen with a -3 charge would have a 1s2, 2s2, 2p6. You may be saying to yourself, that looks very similar, and you are correct, that is similar. And if we add it up, that is 2, 4, and 10 electrons, and our good friend neon is 10 electrons, right? And that is 1s2, 2s2, 2p6. So you could write neon for this guy. You could write neon for this guy as well. And all three of these things, magnesium with a +2 charge, nitrogen with a -3 charge, and I guess I should have put the E there to make it neon. Neon with a 10 electrons and no charge. They all have the same electron configuration. And things with the same electron configuration, those are what are known as being isoelectronic with each other. It's the same electron configuration. Now, out of all three of those things, the thing without the charge, which is neon, is a noble gas. And the one thing that we talked about in terms of noble gases is they're chemically inert, they're very stable, and as we'll talk about when we talk about bonding and nomenclature and all that, this is really the whole purpose of bonding, both ionic bonding and covalent bonding, is everybody really wants to get just like the noble gases. So the way metals and nonmetals do it when they come together is metals will lose electrons and go backwards to the noble gas that came right before them. So if you look on the periodic table, magnesium going back 2 spots takes you to neon. you look at sodium, sodium makes a +1 charge, which means it also has 10 electrons, which moves it back 1 spot to neon. Nitrogen moves ahead 3 spots by gaining those electrons, goes from 7 electrons to 10. Oxygen normally forms a -2 charge, pulls it 2 spots forward to neon's configuration. Our representative elements, the guys in groups 1 through 8, the metals typically will lose electrons and end up at the noble gas that came before them. The nonmetals will gain electrons and end up with the same electron configuration as the noble gas that comes after them. And that's really the whole basis of bonding, and both covalent bonding and ionic bonding. Everybody really does want to end up as those noble gases. Question on things with charges, representative things with charges. Okay, so let me go through a bunch of my blank slides here, I think. There you go. So we're going to talk a little bit about the periodic table next time, I think. We talked about sort of this idea. This is what's known as the Aufbau principle, and it's really just the idea of what we've been talking about with electron configurations is what's sometimes referred to as the build-up principle. So if you look at the periodic table, atomic number increases as you go across the periodic table back and forth. It's a build-up of positive charge in the nucleus, and electrons are added to the atom the same way. We build up that negative charge, lowest energy first, next lowest, and next lowest. So we add those electrons one at a time, sort of like the build-up principle that we have with the nucleus and protons. And we talked about electron configuration for oxygen. We talked about Hund's rule, which again, Hund's rule is maximum parallel spin. So that's why when we have multiple orbitals in a subshell, one at a time in the same direction before they come back and pair off. We talked about orbital diagram. I know, I just had some empty slides. I went for it. There's a much prettier picture of everything we talked about. It is like a deja vu moment. I understand. Let's talk a little bit about valence electrons, which we didn't talk about. But valence electrons really are the highest energy electrons that you find in an atom. Their electrons are in the highest energy level, which means that they're furthest away from the nucleus. They're also the ones that are not going to be held as tightly because of that. And as we will see when we talk about bonding, they are the ones that are involved in bonding. So they're the furthest out there. They're the first ones that come in contact with each other when atoms come in contact with each other, furthest away from that positively charged nucleus, so not going to be held as tightly. They're the ones that are involved in bonding. When we write an electron configuration like we have here for our oxygen, we have 2 electrons here on the first energy level. Our n equals 1. In terms of our second energy level, our n equals 2, we have a total of 8 electrons that are present. And that is here and here. So they're both on the second energy level. There's 8 electrons, and these guys would be the valence electrons. These electrons that are not the valence electrons, that are closer to the nucleus, these are sometimes what are referred to as core electrons. So core electrons are those electrons that are closer to the nucleus. They're not involved in bonding. It really is the valence electrons that are involved in bonding. Again, you could just look at the electron configuration, figure that out. 1s2, 2s2, 2p6, 3s1. This is our good friend sodium we were just seeing. And we have 2 electrons on the first energy level, 8 electrons on the second energy level, and right here we have 1 electron on the third energy level. So sodium would have 1 valence electron, which would be the 3s1, this electron right here. The rest of them would be as core electrons. Now you could do that. You can write the electron configuration and figure it out, but there's a much better way of doing it, and the number of valence electrons equals the group number on the periodic table. And that's for representative elements. So when you look at the periodic table, 1, 2, 3, 4, 5, 6, 7, and 8. Skipping again our transition metal region. Everybody in group 1 has 1 valence electron. Everybody in group 2 has 2. 3, 4, 5, 6, 7, and 8. Transition metals, which are right here, a little bit different. We're going to talk about those in just a second in terms of their valence electrons. But our representative guys, group 1 through 8, the group number equals the number of valence electrons. So here, sodium is group number 1. It has 1 valence electron. If you look at magnesium, which we just wrote the electron configuration-ish for, group number 2 has 2 valence electrons. If you looked at fluorine, it is group number 7. It would have 7 valence electrons. And again, that's just a much easier way to figure out the number of valence electrons. Is just go by group number. And again, our valence electrons is the highest energy level electrons. Question on that there. Okay. Now, you can, if you have a periodic table in front of you or near you, you could actually count off electron configuration on the periodic table. And that is because the first 2 groups on the periodic table is our S groups, or our S block is referred to. So this is our S block right here. And S orbital could hold 2 electrons, so that is 1 electron and 2 electrons. Groups number 3 through 8 is what is referred to as the P block on the periodic table. And P subshells could hold a total of 6. That is 1, 2, 3, 4, 5, and 6. D is here in our transition metal region, is the D block. And D subshell could hold 10 electrons. So that is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And F could hold 14 electrons. I guess I'm going to count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14 electrons going there. So that's our F block and our D block in the middle. So literally you can use the periodic table and the period numbers. These period numbers will equal the N number. So that's like 1s, 2s, 3, and so forth coming down. So for example, let's look at sodium, which is right here. That's sodium right there. I'm going to clear out some of this stuff here. You can actually see what I'm running. We'll kind of clear it out so we can count it off. All right, so if we wanted to get to sodium, for example, and we want to use just the periodic table to do so, we would start up here. This is period number 1 going left to right. This is 1s1 on hydrogen, 1s2 to helium, which is over here. Coming down to period number 2, this is now 2s1, 2s2. Coming across here, this is now the P block, still on number 2. 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. Zigzagging now to number 3. We're stopping right there in the first box. That would be 3s1. So again, for our sodium, like we were saying, 1s2, 2s2, 2p6, 3s1. And you can literally count off the electron configuration from the periodic table, provided you actually know what you're doing. That would be a good thing, because there is a little things that are different. For example, this is the 4th period, and this is our D block. And if you remember from our quantum number talk and everything, the D orbitals don't appear until the n equals 3 level, which means although this guy right here is sitting in the 4th energy level, this is actually 3D. This is 4D, this is 5D, and 6D. So you can see that the D block is 1 off of the period number. And if you remember down here, which is our F block, The F's don't appear until the 4th energy level is when we first start to see the F's. And that means that this guy right here is technically 4F. This guy right here is 5F. And if you remember, as this arrow shows, this first row actually goes here, which is 2 behind the period number. So there is some places where if you're not really sure what you're doing, you might run into some trouble. I would highly recommend just following the zigzag arrow thing that we were using, and you'll be fine. If you want to kind of double check yourself, you can this way. But you know, there are some places where it might get a little bit crazy. So for example, again, just to show you how you could do it, if you did iron, which is right about here in this box, you could count it off again, 1s2 to here, 2s2 to here, 2p6 all the way across to there, 3s2, 3p6 to the end, 4s2, and now 3d here. 3d, 1, 2, 3, 4, 5, and 6. And you can count it off and you'll be fine. Again, you just got to be a little bit careful on some of those things. Question on the periodic table, using it to count off the electron configuration. Again, I would probably just use it more as a backup or a quick way to do it, just to check yourself. Okay. We've done a bunch of electron configuration. I'll just scroll these on the screen in case you're bored and you want to do them. That's a huge one, the EU. That is far, far down there if you want to write that out. But I think we did enough of these so far. So let's just get to a couple other things to finish it up for tonight. Let's just talk really about the transition metal and the electron configuration for transition metals. Transition metals, as I just showed you sort of on that periodic table, is the D block. So transition metals will basically be where you get into those d orbitals, and they typically have incompletely filled d subshells or give rise to cations that have incompletely filled d subshells. Now there's actually 2 exceptions. There actually is more, and we'll see it in just a second, but there's actually 2 exceptions to electron configuration that is different than you would predict based on sort of our zigzag method that we've been using. And it's in that first row transition metal region. It is chromium, which is number 24, and it is copper, which is number 29. So these are 2 exceptions in terms of the electron configuration on how you would write it. It has been found to be more experimentally stable in this configuration. And just if we look at chromium, which is 24, and again, if you follow that zigzag thing, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4, 2, 4, 10, 20, 24. This is what you would come up with. Now, as we've been talking about, the 4s orbital and the 3d orbital are super close in terms of energy. And what they have found is, experimentally, chromium is more stable with an extra electron up in the d orbital and 1 less electron down in the s orbital. And it's just been found experimentally that way. You can also look at it and see we are maximizing a lot of parallel spins, right, which is 100 joule. So this is going to be a little bit more stable. So the exception is right here, extra electron over there in the D, 1 less in the S, and then what we got on the bottom of the screen here is the correct electron configuration for chromium. Copper does pretty much the exact same thing. It has 1 less electron in the S, 1 more electron in the D, and what that's going to do is essentially kind of fill up everybody here with electrons in the D. So it will fill everybody up and have that 1 kind of unpaired electron in the S. So these are definitely 2 exceptions that you should be aware of. And if you look at where chromium is and copper is on the periodic table, and you go below them, there's a lot more exceptions. There's actually some that have no electrons in the S. They've all been sort of promoted up to the D level. And I think I got some of those coming up on the slide, yeah. And we'll come back to that in just a sec. Let's take a look at these guys here. And here's some more examples of that. And again, a lot of these can be found sort of underneath copper and chromium on the periodic table. On the left is what you would expect it to be based on that zigzag approach. And on the right here is what has been found experimentally. So there's our chromium and our copper. Again, you can see this guy here has a similar exception, extra electron up in the D, one less in the S. You can even see palladium down here has no electrons in the S. They have all been promoted up to the D orbitals down here. So again, there's a number of sort of exceptions. Silver, believe it or not, is also an exception. It has a similar one with an extra electron up there in the D, one less in the S. So there's a lot of variations in terms of electron configuration, especially in that transition metal region. For us, I'm going to go with just these two, which is normally what we, now that I've circled everything on the page, you could clearly understand which one I'm talking about. But let's go with this one here. I'll put some stars, make it pretty for tonight. There we go. So we'll go with those two. Chromium, copper, you do need to know the exception to. You should be aware, again, that there's others in the transition metal region, but for the purposes of this class, if you want, you could just follow the zigzag on that guy and write it like we would expect it to be. Just be aware that obviously some of that might be wrong, especially around silver and those guys. But definitely for us, chromium, copper, you should know the correct electron configuration. And again, if it's something that's underneath there, you could just write it like there was no exception, knowing in your heart that there could be an exception and stuff like that. So any questions on the exceptions? What we did skip was sort of the idea of what actually happens when, I'll borrow some of this page, I think. What happens when transition metals actually lose electrons. And what happens when transition metals actually lose electrons is it has a lot to do with how close those orbitals are, the S's and the D orbitals that we've been talking about. So what happens when electrons go in, as we talked about, the 4s orbital is lower than the 3d. They are super close in energy. But as we talked about, once we start actually putting electrons up into our d orbitals, what ends up happening is we do get this switch in terms of the energy. And as I mentioned earlier, the 4s actually becomes higher in energy and the 3d becomes lower in energy. And this is why earlier I was speaking about sometimes people will write electron configuration based on energy. And there are some people that believe this really much, very much. And that's why it kind of goes in order. But you should write it in filling order. But this truly does happen. And what this affects is actually transition metals. So when somebody loses an electron, so we talked about sodium a second ago, when it loses that electron from its no charge, 1s2, 2s2, 2p6, 3s1, it loses this usually the last electron in the row there. And that's usually what happens for it to happen and become positively charged, are the nonmetals gain electrons in that last orbital. In transition metals, something different does occur. And because we have this sort of switch in energy that occurs, when transition metals go to lose electrons, the very first electrons they lose, especially that first row transition metals, are these s electrons. So they lose these guys first. And then if they need more electrons to be lost, then they go down into the D and start taking out electrons. So what happens, for example, if we took something like iron that we just counted off, which is number 26, and iron with no charge has this configuration, Now, when iron gains a +2 charge, it ends up with 24 electrons as it lost 2. And you may be tempted, based on electron configuration, to take those electrons out of the D. But what's going to happen is, because this is a transition metals will always lose those S electrons first. So they're actually going to lose these electrons first. This is what's going to come out. Because again, once we get those D electrons in there, the S is actually higher in energy. And that will give us an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. And again, or if you wanted to do your noble gas configuration, it would be argon 3d6 in this case. Now, if iron went to iron with a +3 charge, it would now have lost 3 electrons from its normal state and end up with 23 electrons, which means it again is going to lose these 2 electrons first, but that's only 2 electrons. The third electron would come out of here at that point, and we would end up with argon 3d5 in this case. So transition metals are different than sort of your representative elements. When those transition metals lose electrons, they always lose those S electrons first, and then if they need more electrons, they go into the D. And that goes true for, where's that periodic table we're looking at there? There it is. That goes through for every transition metal row that we have. All these guys here, the first electrons lost are always the S electrons, and then they delve into the Ds if they need it. So they're always going to lose those S's first, and then into the Ds. So why don't you try one? Let's say we had nickel with a +4 charge. What should the electron configuration be? And nickel with no charge is 28 on the periodic table. Okay, so nickel with no charge is 28. So just to show you the one with no charge, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d8, if I'm not mistaken. So that's 10, that's 20, 28. Now, nickel with a +4 charge means it lost 4 electrons, which means it should end up with 24 electrons. Again, when it goes to lose electrons, it's going to lose its S electrons first because it's a transition metal. That is only 2 electrons though. That also means that we need to take 2 electrons from here And that's going to leave us 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. 2 from the S, 2 from the D are again argon 3d6. Would be your shorthand notation there of it. Question on transition metals, how to write electron configuration for transition metals when they lose electrons. Again, the key there is always going to lose those S's first and then into the D's if you need. Any questions on that? There's clearly enough torture for one night, right? Any questions? Thank you for not laughing too much. I appreciate it. Any questions on anything that we talked about here? That should set us up pretty good. We'll finish periodic trends on Tuesday. We'll go into experiment 3 on Tuesday. Other than that, I'm good. If you're good, don't forget to turn in the lab report if you haven't done so tonight. If you're good, have a good night, have a nice weekend and all that good stuff. I'll see you on Tuesday. And just look for one thing before everybody jumps off real quick. I am going to put up online, I don't remember if I mentioned to you guys or not, but I'm going to put up online a practice quiz for proctorial that we're going to use as a proctoring program for quizzes and exams. So it's not going to be like a real quiz on, it'll just be pretty simple questions. It'll be graded on completion, but it's more so just an exercise so you get an idea how to set it up if you haven't used it before, and make sure you got it all good to go before we take something that's real, like a real quiz or a real exam and stuff like that. So the next day or so on Canvas, you'll put out an announcement as well. That will pop up there. And again, it's not going to be graded for content, but just completion and stuff like that. Now I'm officially done. Have a good weekend and all that good stuff, guys.
Thank you, and enjoy your weekend.
Thank you. You too. Have a nice one.
Thank you.
Thank you, Professor Evron.
Thanks, you guys. Have a good weekend.
Thank you.
Thank you. Have a nice night.